So, welcome to our talk, LPEPM, tricking Microsoft EPM to do our bidding. My name is Rotem Salinas, and this is Tsukerman, and we are both senior security researchers at CyberArk Labs vulnerability research team. So, before we talk about some bugs, let's begin with some background about our target and why it exists. So many organizations these days fall into the everyone's an admin paradigm in their Windows environments. This means that most, if not all, users in the organizations are local administrators on their machine, and they can install any software on their machine, change their machine settings, uninstall any EDR software if they want to, and even run malware on their machine if they fall into some trap. This situation where users have excessive permissions is unnecessary, usually because they only need to do specific tasks as admin privileges. And that's why we have EPMs. EPM stands for Endpoint Privilege Management, and its main purpose is to allow an organization administrator to define a set of policies and rules that allow an unprivileged user to run specific programs as an elevated user with administrator privileges. The main benefit of an EPM solution is that they don't need to be local administrators on the machine, and they only need the rules and policies that will allow them to execute programs that need elevated privileges. So this is how it works. Microsoft EPM is an add-on to Microsoft Intune, and an administrator would log in to the Intune panel, go to Endpoint Security, Endpoint Privilege Management, and create a new policy. The policy will be stored in the cloud and will be pulled into the machine during the sync operation, and then stored locally both as a file and as a registry values and keys. And then, after that, the unprivileged user can click on an executable, click on the run with elevated access, and a shell extension will create an IPC request to a named pipe that a service named EPM service opens, and the elevated process will run under a virtual account, which will have the naming convention MEM/domain name _ username _$. And a virtual account is basically a temporary administrator that is created just in time. So while we reverse engineered the EPM system, we came up with this architecture. And let's take a close-up look. So the first component is the EPM shell extension.dll, which is a shell extension which is actually a COM server that extends the right-click context menu with the run with elevated access button. Then we have the EPM client stub, which is a .NET executable binary that is invoked by the shell extension and communicates directly with EPM.exe through a named pipe that his name is randomly generated and saved into the registry to initiate the elevation of a target program. Then we have the EPM service, which is also a .NET executable binary. And it's the system's main component that mainly handles IPC requests, both creating and listening on the named pipe, and handles the elevation of the program, and it also handles the sync operation from the server. And this service is running under the user entity authority system. Then we have a device driver, memepm agent.sys, which is responsible for monitoring new process creation, and we can also communicate with it with filter communication ports. Then, almost finally, we have the EPM service stub, which is also a .NET executable binary that's used when virtual accounts needs to be created during the elevation process. And EPM consent UI, which overrides the consent UI of the user account control with a dialog for EPM. And finally, we have EPM interop, which is a native dynamic link library binary that exports functions critical for the elevation process and consumed by both EPM service, EPM client stub, and EPM service stub. So that's the whole architecture. Then when we create an elevation rule, the settings looks pretty much like this. It basically has several properties, including the file hash, the elevation type, which in this case is set to automatic, but could be either deny, which means deny all the elevation requests, support approved, which means that an administrator will have to confirm each elevation request, or user confirmation, which means that the user will have to confirm, the child process behavior, which in this case is set to allow all child processes to run elevated, which means that all the child processes will be elevated as well as the parent process. Deny all or require a rule to elevate. We have the file name and the rule name, which are self-explanatory. The file name is the target programs that we want to elevate file name. And there are also other fields like path and certificate and original file name that are not mandatory. And this is basically how the dialog that shows when denied elevation happens. So now that we know what's EPM all about, let's look for some bugs. So I began my search while reverse engineering the EPM service binary, and I was looking for a function that was handling the hash calculation. And I came upon this function called get elevation result. And while looking at it, I found this line, get matching rule that is assigned into a match result. And then after that, in line 105, we can see that the match result has a member called computed file hash that is being assigned into the file hash property of the elevation result. And I felt like I found a function, and basically I got to the conclusion that get matching result basically calculates the hash and compares it with the hash of the target application that we want to elevate. Then elevation result is being returned into a different function called resolve. And if we look closely, the call to get elevation result is being returned as well to a different function called process message. And process message, the call in process message to the resolve function is being assigned to another elevation result variable, and then assigned into a request class or object, which is then passed to the process elevate type and launch elevated process function. Now, has anybody been to Mickey Jean's presentation yesterday? Please raise your hand. Okay, this bug might look familiar to you. Can you spot it? Anyone? Okay, so this is a time of check to time of use bug. Basically, the second calculation of the target file for the hash happens in the time of check. Then the time of use is the actual call to anti-create user process that happens inside the process elevation type and launch elevated process. This means that if we win this race condition, we could possibly effectively achieve a local privilege escalation from an unprivileged user to an admin. So again, this is a talk to vulnerability, and the effect of it is that any defined elevation rule could allow an attacker to run any program or application in an elevated state. And in this diagram, we can see the double fetch that happens. First, EPM service is calling grid file on a file that we have an elevation rule for called TCP vcon64, which is the hash calculation. Then EPM service tab opens the file under a virtual account, which is a privileged user, then reads it and creates a process from it, which is the time of use. So to reiterate, our exploit will work in the following manner. So the attacker will request the execution of a binary path with an elevation rule. Then the time of check, EPM service will open the file, will hash it and check against the elevation rule, and then proceed with execution if it's okay. Then the attacker will replace the file at the execution request path with its own malicious payload. Then the time of use, EPM service will create a privileged virtual account just in time and calls create process on the request path, now containing the malicious payload by the attacker. And finally, the attacker will stare smugly at the screen while the elevated payload executes. So let's see a quick demo of that. So we're starting with an unprivileged user, and we are checking its integrity level, which is medium, and it's not a member of the administrators group. Then we check the hash for our target application, which is TCP vcon64. And we will try to run it with elevated access, which should work as usual. This is with high integrity and the virtual account. Now let's try it with a different application which we don't have an elevation rule for, like PowerShell in this case. So run with elevated access and we get the denied access. Now let's check the hash for PowerShell also, and we'll see that they're obviously different. And now let's run our exploit. The exploit gets the interval. So in this case, it's 55 milliseconds for this specific VM. And immediately we get an administrator shell for PowerShell. Let's check our integrity level. We see that we are under the privileged virtual account with the $sign at the end, with high integrity. Yes, and we are part of the administrators group as well. Great. Thank you. So Microsoft assessed this issue as important, and a patch was released, but a CV was not assigned for some reason that is beyond me. And at this point, I'll give it up to Philip, that will tell us all about the second vulnerability we found.
Hi. So people can't really have nice things, which is why Microsoft tried to make this vulnerability unexploitable using a couple of different steps. First of all, we're using file sharing disposition. Whenever someone opens a file in Windows, they can supply a sharing disposition, file share read, write, or delete. That allows other subsequent file opens to open this file with the same rights, meaning that even if you're allowed to open a file for writing if the file is already opened without file share write, you will be unable to open this. Same thing goes with delete and read. So now Microsoft EPM starts opening the files for hash validation with share read only, meaning that you can't overwrite the file, you can't delete it, and you can't move it, because moving is pretty much deletion because, well, the file does not exist in its original location. Another part of the steps taken to make this unexploitable actually existed before, but before it was kind of useless, and it is final path validation. There's a Windows API called getFilePathNameByHandle, which does exactly what it says. It traverses all kinds of symlinks, etc., and gives you that final actual location where the file is located. And this is validated several times to see that no rugs were pulled along the flow. And the final part of the patch is now an addition of another file hash validation step to the process creation notification routine in the EPM driver. Now, this happens after the process is launched, and instead of traversing the path again, it actually uses the file object that's attached to the process, meaning that, well, that's specifically the same exact file that's being used to run the process. So now we can't really move or delete the original file because, again, sharing disposition, share read only. Final path validation means that it's significantly harder to do any kind of path redirection shenanigans, junction folders, or symlinks or whatever. But we could have tried to play around with that and solve this, but the biggest problem we have is the driver callback. We had a time of check, time of use vulnerability, and now we have a check after our use, meaning that, and it checks the same exact file, meaning that even if we are able to create a process with a payload and pass that validation, it will get validated again and never run, which is not very fun. So the flow right now looks like this. We try to request the execution of an allowed binary. EPM service opens the file exclusively, hashes it a couple of times because the way to fix a double fetch is making it, I think it's a quadruple fetch now. And it creates a virtual account and calls pretty much create process on that request path if all validation steps are completed. And we're sad because we were unable to replace the file with anything else. The file is hashed again just to make a sanity check that, well, we really didn't replace that content with anything, and we are still sad because our entire self-worth is hanging on this one exploit working. And this kind of loss, we did what many others try to do when they feel this kind of loss, which is resort to necromancy. We want to revive this same exact LP vulnerability, meaning that we want to abuse the same exact double fetch or n fetch, whatever now, to make disallowed binary execute as elevated. And to use this, we're going to use the Cloud Sync engine in Windows, which is a Windows feature that's powered by mostly the cloudfilter.sys driver. It's a file system mini filter driver that's pretty much the things that's responsible for you clicking on a file that you have on OneDrive and you never had on your machine, and that file suddenly having content and being read transparently without you doing anything else. So this is implemented using placeholder files that only have metadata and no content. User mode provider process can be responsible for a folder that you own, and every time a placeholder in that folder receives an IO request, you get a callback in user mode that tells you, hey, this file is getting read, and this range in the file is actually unavailable. The bits just don't exist on disk. And then you can provide those bits. Now, to do that, and to do that transparently, so that the first time you double-click on that OneDrive file, it magically appears, this hydration and dehydration, meaning that filling the file with content and removing the content again, it needs to be able to bypass sharing disposition completely. So that first part of the fix suddenly becomes less relevant. Now, this is of course perfect for our type of race condition, because the entire fix was assuming that a read-only handle, an exclusive handle to a file, is indeed exclusive, meaning that the file itself is immutable, and we can make it mutable. And this kind of trick was discovered by Gabriel Lando of Elastic and James Forshaw of Google, and a side effect of this is making the race condition a bit more complex, because now every time of check or time of use, every single fetch, isn't every time you open the file and receive a handle, but actually every single I/O request that you get to a non-existent part of the file. And to make this thing possible, or at least plausible to win, we have a secret trick, which is the process info structure that's used by the sync provider. Whenever you receive a callback that tells you, hey, this file needs bits, we need to satisfy an I/O request right now, you can configure your provider to receive process info. The process info structure tells you exactly which process with which PID and which command line is trying to read this file, which lets you decide, well, I'm going to show this process those bits, and I'm going to show another process different bits. And now we have this kind of possibility to do complex heuristics, and instead of doing a pure race condition in which we try to either flip between different versions of a file endlessly in a loop, we can choose which kind of bits we show which request. And we have this generalized flow to this kind of vulnerability. So we start with a dehydrated placeholder, and every time we receive an I/O request, we can do heuristics. We can say, oh, this is a validation request because this is the EPM service process, and this is the first time it tries to read the beginning of the file, so this must be a hash calculation. So we provide the good bits. And this makes the validation pass. Which is quite nice for us, because hash validation here is actually a series of small subsequent reads. So if you continuously flip between versions, you will probably lose this. You will probably lose this race, because while you flip between versions, part of the hash calculation is going to see the bad file. So the probability that you win this race condition is really low if you treat it as an actual race condition. And immediately after you provide the bits, you dehydrate the file again. So again, there is no content on disk. So the next I/O request will be forced to go through your callback again. And we do this again and again and again and again until we reach that process creation bit, and we say, okay, here's a payload. And this payload gets loaded into memory, and now you have a process that's backed by your payload. Now, when the driver tries to read that file again, and it's all the same file, again, it's empty. It goes to our callback, and we can provide the good bits again. So, again, with our specific flow, we ask the EPM service to create a placeholder, to run our placeholder. EPM service opens the file, tries to hash it. We give it the good bits and dehydrate immediately. It locks the file and checks it again, including a final path check. And we give it the good bits and dehydrate again. The file is at the same path, at the expected path. It has the expected hash. Everything is nice. So we can create a virtual account and create a new process. And now we get this callback again in user mode, and we can say, okay, here's a payload, here's a file with some shellcode. There's a couple of interesting payload considerations here because of weird memory manager quirks, but please ask us about this after the talk. But when the driver tries to validate the file again, it's empty again, and we supply the good bits again. So we don't crash, we pass every single validation check of the hash, and the only thing that sees the payload is process creation. So now let's see how the exploit just looks. So good file executes and elevates. Bad file does not execute and does not elevate. So let's create a placeholder that will try to control and pass all validation checks. And there's a bit of a delay because we override the file a couple of times, and hooray, we have an elevated command prompt. Yeah. So we still can't have nice things. And Windows 24 H2, which is right now the most recent supported version of Windows. There's a couple of others that are still supported. They still get security updates where this works. But Windows 24 H2 kills the exploit. It kills it because there's been a change in NTFS that makes it impossible to override the file using the same trick that Cloudfilter uses when there's an image section attached to the file, meaning that whenever you load the file as an executable, you create a process, you load it as a library, this whole thing becomes impossible. So that last hash validation, we can't really pass it. But again, we still want to have the same exact LP. So what if we change our target a bit, and instead of trying to go smarter and more complex, we try to go dumber and simpler? So Microsoft EPM allows for installers and PowerShell scripts to be elevated as well. So if you have a rule that elevates some kind of PowerShell script or some kind of installer, we can try this as a target. And those aren't processes, those aren't DLLs. They won't ever have image sections. So the exploitation becomes much simpler. All we need to do is to create a placeholder and ask our exploit code to supply the bad bits whenever PowerShell tries to access the file for the first time. Now, that point in time means that PowerShell is executing, which is after all validation steps have completed. So we don't really need to flip between different versions of the file anymore because, well, we know that everything apart from PowerShell should see this file as benign. And we provide the payload to PowerShell. So everyone sees a nice file, PowerShell sees our malware, and it's getting executed as admin again. Of course, we found another set of vulnerabilities or security issues. First of all, UNC paths and remote paths are supposed to be forbidden because, again, the fix for the vulnerability depends on the file being the same every time you access it. And when the file is in another machine, another person owns that machine. So they can provide different bits every time there's an IO request to that file. The problem is that the code that tries to deny access to UNC paths is actually in the EPM client stub, which is something that's run in the regular user context and just communicates with the EPM service. And client-side security controls mean nothing when client-side is the attacker side. So we can just implement the same protocol ourselves and say, okay, here's a UNC path, and then do the same vulnerability. Instead of using the cloud filter, we just use our own SMB server. So again, another variant on the same vulnerability. And let's have a slightly different vulnerability in the form of DLL hijacks. Usually DLL hijacks aren't really security vulnerabilities because this means that, well, if you're able to run code, like if you're able to run arbitrary code, then you can run different arbitrary code in the context of that arbitrary code, which is not very interesting usually unless you're trying to like hide from EDR, because this runs in the context of your own user. But here we have a nice little product that takes a piece of code and gently pushes it through a security boundary. and everything that it comes with. So that means that every single DLL hijack on a process that you can elevate using EPM becomes another LP, which is nice for us. And also MSI handlers or installers are vulnerable as well, just in the same way that PowerShell is vulnerable. So we tried to disclose this to Microsoft, and it appears that we can have nice things because everything we've said after the first vulnerability is a no fix. They've decided that this is a moderate severity issue because this requires user to this requires some permissive configuration of the product, and they've decided to clarify a couple of stuff in the documentation. So let's take a quick look at the documentation. When we look at the certificate rules, we do see that they strongly suggest using path if you only have a certificate in a file name, simply because, well, if you have everything signed by Windows and called and called Notepad, you can change CMD to a Notepad and then you can elevate CMD. So a path is nice. But, and let me just quote this verbatim, file hash rules are the strongest rules that can be created with Endpoint Privilege Management. These rules are highly recommended to ensure the file you intend to elevate is the one that is elevated. So, the recommended usage right now, is everything we've shown now to be vulnerable, and it continues to be vulnerable. But there has been an addition. Now there's a suggestion to require file path restrictions on all rule types. So when configuring an elevation type, you should specify a required file path, because while optional, it can be an important security check for rules that leverage automatic elevation. Now, that's a weird way to say that if you don't do that, you have an LPE in a product specifically designed to prevent LP. And also this completely works on both user-controlled elevation and support-assisted elevation, so you should do this always, and if you don't do that, then you lose. So, to reiterate, you're not vulnerable if you've read recently this updated documentation and you've decided that the suggestion is a must-have. All of your elevation rules, not a single one, should exist that's without a path, and that path is specifically inaccessible by unprivileged users, and it already exists, meaning that if you can create that path, you can put something in that path. And of course, because the code integrity component of this entire validation flow doesn't work anymore, or it never worked, you need to know that there's no bypass for the path component of rule validation, and of course there's no vulnerability in that. We have not found anything. And otherwise, you basically have a no-fix LP in your network if you're using this product. So to conclude, one patch, several bugs, 0 CVs. And that's it. If you have any questions, you're free to ask. I think we have like 5 minutes. And we've actually released the first part of a blog series on this research. It contains the first vulnerability, the reverse engineering process on Microsoft EPM, and the exploit code for the first vulnerability. Thank you very much.